All right, so this is a recording on analog to digital conversion, and here I'm trying to cover some of the basics of the A to D conversion, and we'll get to some specific circuits that try to scale the voltage levels and so on. And then I'll leave most of the PIC specific details to, when we discuss it in class. So here I'm showing the same signal, same analog signal, and the time on the x-axis you have time, and this could be microseconds. These dashed lines could show microseconds here, and the y-axis is the voltage, the input voltage, which is an analog signal, and this top line is your VDD. Now, if you're using a device that uses 5-volt VDD, then this would be 5. If you're dealing with a 3.3-volt device, then 3.3 would be the upper voltage level. And here, I just want to see, basically, in the real world, in the physical world, signals are analog. So you have a temperature sensor, you have a light sensor, you have a microphone, whatever that you have, whichever of these devices that you have, the signal that is coming in is going to be an analog voltage, right? And the analog voltage could be any value, any real value between 0 and VDD. But then when you want to process it, you have to convert it to digital, to binary values, right? So if you use a conversion mechanism that basically says, take one sampling period and take the average value of the signal, and if that average value falls, if I divide it into the number of segments that you have here, then if I divide the voltage value, the real voltage value, by these numbers and truncate it, then that will be the value that I'm dealing with. Okay, so here the corresponding, so if you're talking about a, let's say, 3.3 volt, okay, and here is your 0 volt. I'm not going to do the calculations to tell you, what these voltages are. We'll do that later. But the corresponding values that you're going to map to would be 0, 0, 0, 1, 1, 0, 1, 1. Okay? So any value that is between this voltage, less than this voltage, and this voltage would be mapped to 1, 0, which is number 2. Okay, so if I feed this to an analog to digital converter, it's going to look at the average values in this range, and it's going to be the averages. I'm assuming that this crosses this point after the 50%, so the value that you're going to get is going to be 0. Then in the next time scale, your average value seems to be within this range. So this is the value. So this is going to be my signal so far. And here your average value would be here. It would be here. Would be here, right? So here's the digital form of the signal that you get. And here again, let's assume that this is less than, right? This is, more than half of the time it's on this lower value, so it's going to map to here. Here, let's assume most of the time it's on this uppercase, right? And here, let's assume that most of the time it's down here, and then it's going to be up here. So note that your 3.3 volts that you reached here is going to map to 1, 1, which is number 3. Right, and then this is going to be a value of 0 and then a value of 0. Okay, now if you look at the digital signal, the resolution in time is called the sampling time. So your sampling time, if I assume every dashed line is 1 microsecond, is going to be 1 microsecond, one sample per microsecond, or 1 megahertz sampling. And if you look at the levels of the value that you have, this is called the A to D resolution, or the value resolution, right? Now here I have exactly the same signal with exactly the same timing, but here my voltage level of 3.3 is now divided into two levels, right? So this is going to be 1.6 whatever, the half of 3.3 volts, and here is going to be the values that I have in my voltage. All of these are going to be up here, right? And same as here, same is true here. Then I have a 0 here, I have a 1 here, I have a 0 and a 0, right? So the values that you have is 0 and 1. I only need one bit to represent it, right? So the number of segments that you create are going to be 2 to the k, k being the number of bits that you use here. Okay? Now, so this talks about the different values that you have. So if you look at the digital value that you're going to read is going to be 0, and then 2, 3, 3, 2, 1, 2, 0, 3, 0, 0. Here you're going to read 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0. Now, here on the bottom figure, the number of levels that I have is the same as the figure above it. So here again you have the values 0, 1, 2, 3. Here you have the values of 0, 1. But now the sampling time is one sample every 2 microseconds, right? So this is not going to be a 1 mega samples per second. Is going to be 0.5 or 500k samples per second. So here again you would take the average value, and I'll talk about the physical averaging. The physical averaging is done using a capacitor, but we'll get to those details later. So here if I assume that the average value, I don't know, maybe let's say the average value falls somewhere along here, right? So this is going to be my value. So I'm reading a value of 1, and then here the average value is going to be 3. Then let's say the average value within this range is somewhere around here. So this is going to be the value that I have 2. The average value here, let's say, is, I don't know, let's say here. And the average value here is, the average value, let's say, is here. So I get this value here, and then the average value here is going to be 0, right? So the values that I get are going to be 1, 2, 0. Okay? Now, so in time, you have less resolution, right? So your sampling is done at a slower rate. And I'm not going to do this one. I leave it to you to do it. But you can imagine that it's going to be a bunch of 1s and 0s here, and a number of 1s and 0s is going to be half as many as you would have here, right? So this is the basic concept of A to D resolution in terms of the terminology and the processes. For now, for the rest of the slides, let's forget about this sampling time. Let's assume that that sampling time is a fixed number, and we're not going to worry about it. Let's take 50 microseconds or 30 microseconds, whatever that is. We're not going to talk about that in the rest of this video, unless maybe towards the end when I talk about TAD, time to analog to digital conversion. But for now, let's forget about that. So whenever I talk about resolution, then I'm basically talking about these levels, how many levels I have here, and what does the value mean, the value that I have. Okay. Now, the questions that I'm going to ask in the next couple of slides is going to be, given a fixed voltage, and when I talk about the fixed voltage, I'm assuming I'm talking about the average voltage during that time. So here, if the average here is, let's say, 2.9 volts, then 2.9 is the value that I'll be referring to, the voltage level. So I'll be asking the question of, if my average value is 2.2 volts, which one of these digital values is that going to map to? Assuming, of course, the number of levels that you have, right? So the question that I ask is V in going to a digital value. How is this process done? And of course, the inverse question is, let's say my analog to digital conversion gives me a digital value of 2 out of the values from 0 to 3, right? Then what was the original Vn that I used that gave me that D value? Okay, so let's talk about these issues. So first of all, what is the resolution? Your resolution in terms of volts is going to be your Vmax divided by 2 to the n minus 1, right? So if I have, let's say, 3 volts, and I divide it into these 4 sections, right, then the voltage levels, the different voltage levels that I can detect is going to be the number 3 divided by 2 to the 2, which is 4 in this case. Now, some analog to digital conversions use 2 to the n, some use 2 to the n minus 1, and your PIC is one of those. The PIC microcontroller is going to do 2 to the n minus 1. And the reason that it's 2 to the minus 1, and you can see that from the previous slide, right? Here, we never go to the actual value of 3.3, right? We're always truncating things down to this level. So then in essence, I'm dividing my resolution into 2 to the n minus 1 segments. So that's the equation that we use for PIC. So this is going to be the resolution in volts. Now, what does PIC use? Well, PIC uses, let's say you're using a PIC device that has a 3.3 volt VDD, and it uses a 10-bit analog to digital conversion. So 3.3 divided by 1023 is a number approximately 3.22 millivolts, right? So if you have any signals that has differences in 1 millivolt, you're not going to detect that. Right? Let me go back to the previous slide. Right? So here, if your signal level is here as opposed to here, it's not going to detect it. Right? So it's very coarse in terms of detection, and it's even worse here. So it's not going to detect any difference from here or here or here. Right? So if your signal changes very slowly, let's say it's this much, and then in the next level it's here, and then it's falls down just a little bit. For all of these, you're going to read the same thing. You're not going to, of course, I mean, shift this down here, right? What I meant was if you're doing like this, and then like this, and then like this, all of them are the same to you. All of them are showing you a value of 0, 0, 0. It's not going to detect those minute differences in the voltages. So that's what I mean. The resolution is going to be this. If you're using a 5-volt PIC device, then 5 volt divided by 1023. So for example, PIC 18 uses a 5 volt VDD. Then it's going to be around 4.88 millivolts, right? Don't confuse yourself with this. This is not the device that you're going to use, so don't use that. All right, so resolution. If you look at this, the values from 0 volts to 3.3 volts are going to map to 0, 1, 0, 0, 1, 0, 1, 1. Okay, and then basically if you look at your equations, they are going to be so the digital value that you want to get in terms of the Vin is going to be Vin divided by Vmax, right? You want to know what is the ratio. So if my signal is here, what ratio is it to this number, right? You want to know the height of this line compared to the height of the overall line times your 2 to the n value. Again, you could say 2 to the n minus 1 here. I won't be picky about it. I mean, if you're looking at 1 over 1023 versus 1 over 1024, there's not much of a difference. So you could, in your calculations, put some fudge factor in there and do it. Now, a lot of times your signal doesn't go between 0 and 3 volts, right? Sometimes it goes from a Vmin and a Vmax. So your signal is Vmin and Vmax, right? And if you condition your A to D to map this to 0, 0 and this to 1, 1, or as many bits as you want to have, then your equations become, if you want to do analog to digital conversion, the digital value is going to be now Vin minus Vmin, right? Just subtract that offset, divided by Vmax minus Vmin times your resolution, which is 2 to the n minus 1. Right? This is going to be the value that you would get out of your A to D conversion. Now, this is an important distinction to make. If you condition your PIC microcontroller or any A to D conversion unit to map 0 to this non-zero voltage of Vmin, this is going to be your equation. However, if your signal is never going to be less than this Vmin, so the signal is always changing between this Vmax and this Vmin, but you don't tell that to your A to D converter. You just let it work on its default value. And if this is a 0 value and this is 1, 1, then your A to D would basically work on the condition that Vmin is 0. You will not get the equation that I showed you above. So your D here is going to be Vin divided by Vmax times 2 to the n minus 1. And now, here's going to be the difference. The resolution here is going to be this whole range from Vmax to 0 divided into 3 or 4 equal lengths, right? So your resolution here is going to be your Vmax divided by 1023. But here you're saying, no, don't go all the way down. Divide this range into 4 or 1024 or whatever segments that you want. So here your resolution is going to be your Vmax minus Vmin divided by 1023 or 1024. Okay, so this is going to be important. You're going to have homework problems that talk about this and make this distinction. So you get a higher resolution, better than that 3.22 millivolts, if you condition your A to D to basically map 0 to here. In this case, this would be mapped to, I don't know, maybe 1, 0, 1 or something. So basically you're going to waste a range of your values. You're never going to get the value of 0 in this bottom case. Now the other question that we want to ask is, let's say my A to D in one of these time segments tells me that my signal value, so you have 0, 1, 2, 3. Let's say it tells me that the signal value is 2. This is the digital value. Now, what was the average? So if my D is 2, what is my Vn? Right? That is the question. Now, Vn is not going to be just one value, right? I mean, when you digitize it, when you quantize it, then you lose all the detailed information, right? I mean, your signal could have done a lot of wiggles and going up and down. You would lose all of that information. You'll only look at the average value that it had here, right? So your Vin could be anywhere from 2 times your VDD or Vmax divided by 1023 or 2 to the n, or so this is going to be the range. This is the minimum range, so if the signal is just slightly above this voltage level of 2, but the signal could have been slightly below this, right? So it could have been 3 times Vmax divided by 1023, but exclusive, right? If the value is exactly that, then your signal would have been 2. Okay? So here is a range of values that you're going to see that basically tells you what the original signal would have been, the average value of the signal would have been to give you this value that you have. Okay, so this is about the actual voltages and the actual digital value that you look at. Now let's go and just briefly talk about the timing that you have. So the timing here is going to depend on 2 factors. One is the electric characterizations of your sensor and also your PIC microcontroller, because the way that A2D devices work is that you load the capacitance, you load charges, you put charges on a capacitance inside your A2D device so that its voltage becomes equal to the voltage of the input, the sensor, the input value that you have, right? And it takes time through an RC circuit for that capacitor to charge up. That's called the sampling time. And once you do the sampling, then there is the actual conversion. There has to be some process that says, let's take the charge on this capacitor, let's take the voltage on this capacitor, and let's try to, approximate, what value it falls onto among these levels that you have, and convert it to the digital, right? And that's called the A to D conversion time. In the PIC, you're going to look at both of these values, and we can take a look at the manual and see what these values are. So let me just instead of going to this part, so here on the manual on page 4, and by manual I mean that the chapter 17 that talks about A to D conversion. So here you can see that it says sample time. This is the time that is needed for basically putting charges on an internal capacitor, and this is the A to D conversion time that PIC uses to do the conversion. So more details about this will come later, but what I want to do now is to look at Huang's slides. These were originally meant for PIC 18. We are talking about PIC 24. So just ignore any code that you see here. The code is going to be different. The specifications of the A to D conversion is going to be different. But here, basically, I want to go over some of the basics here. So essentially, in the physical world, you have things like temperature, pressure, light, weight, whatever that is. You have a transducer, and the transducer is basically taking these things, so this could be degrees Celsius, and convert them to voltages, right? Or it could be the candle, or it could be the pound, how many pounds are converted to voltages, and then your digital scale could be doing this, and so on. And then you have a signal conditioning. So that signal conditioning is the one that maps the Vmax to Vmin to your VDD and ground value to feed to your PIC microcontroller. And if you want, you can skip this process and tell PIC directly that this is my Vmax, this is my Vmin, condition yourself. But that has its own costs, and we'll talk about them later. And then the AD converter is going to go through an iterative process of converting that analog voltage into a digital value and then use that digital value in your computation. So if the temperature is too high and the pressure is too high, then lower the heat, reduce the fuel going into the tank and so on. So basically you take some actions based on the values that you receive. Now in an ideal world, you would like to have a linear mapping from your voltages to the digital code that you have, right? But obviously this is not going to be possible. So if you look at the elements that are sensitive to, for example, pressure, take a piezoelectric unit, it's not going to show you a linear behavior, right? So the behavior could be something like this, right? And it's only going to be one section of it that is going to be linear, right? So basically the manufacturer is going to say, I'm going to map from this value to this value, and this is the only place that I can guarantee linearity. Right? Outside of that, I don't guarantee that my device is going to work. Okay, so you're going to find in electric characteristics of the devices that give you, in one region, you're going to be linear. So that's one part. The other part is your A to D unit is going to have limited number of bits to work with. You don't want to wait infinitely long to do the conversion, so you want to cut off the loading of that capacitance, the charging of that capacitance, and also the circuitry that goes into successively coming up with more and more accurate digital representation of it is going to have limited number of stages. So the result of that is going to be you take your analog voltage and you convert it into these steps. Now the maximum amount of error, so if you have VDD divided by 2 to the n, then the maximum amount of error that you might have could be this amount, right? So if my value is just slightly, just a little bit shy of this value, the A to D unit is going to map it to this value, which is going to be off by VDD over 2 to the n. But on average, that doesn't happen, right? I mean, on average, signals could be here or it could be here. So on average, it's going to be half of that. So it's going to be VDD over 2 to the n. Plus 1, right? That's going to be the resolution that I have. By the way, just to make sure that you do not confuse this graph with the graphs that I've shown you on the ones that I did hand drawing, basically this is a different graph. This has voltage on the x-axis. This has the digital value on the y-axis. It's not the voltage versus time that we had. All right, and then the circuits that do the conversion are going to be a bunch of classes of A to D conversion. I'm not an expert on A to D conversion. I don't know how they work, but I just know that the one that PIC uses what is called successive approximation AD conversion method. And essentially the way that it works is it asks, so if you have a 10-bit value, all right, and let's say the voltages that you have or the analog voltages are between 0 and 1 volt. Okay. Now, so this bit, if this bit is 1, it means that your signal is greater than 0.5 volts. If it's 0, it means that it's less than 0.5 volts, right? So the successive approximation registers basically operate bit by bit. So it says, let's take the analog input, and then they convert it to some pre-specified, 0.5 volt value, and it says, is the Vin greater or less than this? And if it says greater, then you put a 1 here, and then do a subtraction of this Vin minus this 0.5 volt, and then they ask the question, is the result going to be 0.25 volts or greater? If it is less than, then you would put a 0 here, and so on and so forth. You go until you have 1 over 1020. Yeah, if you have 10 bits, 1 over 1024 bits, 1 over 1024 volts, and that's going to determine if you have a 1 or 0 here, and that's going to take the value. Now, every single one of these bits is going to take TAD time, right? So to convert one whole 10-bit value, you need at least 10 times TAD to do the conversion, right? And this TAT value you have to pick from the specific pick value that you have. We will deal with this later, how to take the values. And in fact, pick is not going to do 10 times TAT. It's going to do 12 times TAT or 13 times TAT, because it does need some time to reset these devices and the volt and the internal capacitors and so on. So it's going to take 12 TATs to do a 10-bit conversion. And I'll talk about that 13 TAT thing later. So this is the algorithm, and this is what you're going to find in a PIC device. And I liked this. This is from PIC 18. This is PIC 18 specific. This is from the PIC 18 manual. In your PIC, you're going to see that in section 1710, which is this figure. So slightly less busy compared to what you have. And let me explain things here on this figure, and then we'll talk about the more busy figure from PIC 18. So this is your sensor. This is the sensor that you have, which converts, let's say, temperature to a voltage. And it has an intrinsic RS, the resistance of a sensor, and that connects to your AN1 pin, for example, or AN2 pin. Right? Now, there's going to be some capacitance on the chip, the intrinsic pin capacitance. There's going to be some leakage. The transistors inside your PIC are going to leak, and the leakage is going to go higher and higher depending on temperature. The higher the temperature, the more leakage you have. And then you have the RIC, the interconnect, which the PIC manufacturers say we guarantee that it's going to be less than or equal to 250 ohms. And then you have a sampling switch, RSS, which they again guarantee is going to be less than 3 kilo ohms. And when you tell PIC sample the input, it's going to close the switch, and then you have a long RC circuit that needs to load up this C hold. Right? And you know that it takes forever. It takes infinite amount of time for this C hold to charge up to the maximum voltage that you have, or whatever voltages that you have here. So if it's a 1 volt, let me go and scribble things maybe on this one. So if you want the RC circuit to go to 1 volt, it's never going to get to exactly 1 volt, right? It's going to take, this is an exponentially decaying curve, and it's not going to charge up all the way to, let's say your input is 1 volt, it's not going to charge up to 1 volt. But you don't need to wait forever, right? If your resolution, if your voltage resolution is only this much, then all you need is for this voltage to charge up to somewhere beyond this line, right? So in the equations that govern how long you have to wait in the RC circuit, you're going to see things like log of 2 to the n, which basically comes from the fact that you don't need to wait forever. You only need to wait for it to pass through these n levels of conversion, so you can cut it off and say that's enough. So in the calculations, you're going to use the RC values that you have that determine how long you have to wait. So that RC equation that is going to tell you that, which has the logarithm term in it, that has to have some terms that adjust for the temperature. You have to have some terms that take into account this RS thing. All of these have to be added up, and it has to charge up this C hold thing so that you wait enough so that the charge that you put in here is good enough for a 10-bit resolution, so that it can deliver that 3.22 millivolts distinction. All right, and the manual basically refers you to the electric characterization at the end, but doesn't give a whole lot of details. You need to, know a little bit of analog to digital conversion to understand it. Now, PIC 18 gave a whole lot more details in its manual, and it gave detailed examples of how you calculate based on the temperature and so on, and they gave you the models, the electric models that you would go from these resistance values and the temperatures to an RC value that gives you an exact time. So you would plug in the values of this RS, the temperature, RIC, and so on, and it would tell you you need a sampling time of, let's say, 3.3 microseconds or 5.6 microseconds. So that's the sampling time. You need to keep this RSS closed for that 5.6 microseconds or whatever that you need to charge up this enough. And then you would tell PIC, enough with sampling. You clear a bit that says do sampling, and as soon as you clear that bit, then PIC knows that it has to do the conversion, and all the circuitry that does the successive approximation and so on comes after this. They all read off of this C-hold capacitor, so your input signal could go up and down. You're going to be oblivious to any changes that you see there. You're only going to work on this C-hold thing right here. Okay, so and this figure, as I said, is copied from your PIC 18, and essentially, it gives you the C pin value, and it talks about these threshold voltages and so on. For now, let's ignore all of that, but just know that there are equations that tell you how long you have to keep your sampling switch closed to do the hold time. So this is called the hold or sampling time. Okay, and then this talks about the equations that we've already derived. So these are the analog input is converted to digital code using this, and then it gives you the voltages based on the K value and so on. We've gone through that, and it gives you a bunch of examples. I suggest you do go over these examples and do them, and also the reverse of it. So say instead of the instead of giving you the 80 conversion, the digital value of 25, 80, and so on, wants to the reverse thing. So say I got a 1.7 volt or 2.47, and these are all based on a 5 volt. 4 volt here. So if I'm given a 3.35 volt, what value is that going to convert to? And check your results compared to here. All right. Now the conditioning circuits. If you don't want to tell PIC to just go from, let's say, 3.3 volts to 0 volts, because maybe your external signal is going to go only from 0 volts to 0.2 volts, right? If your sensor only gives you up to 200 millivolts, and if you ask your PIC to divide this 3.3 to 0 into 1023 segments, then you're basically wasting the capabilities of your A to D conversion, right? You're not going to get a 10-bit resolution here. You're going to get only 0.2 divided by 3.3 of the range. So if a full signal from 0 to 3.3 volts, so 0 to 3.3 volts would give you from 0 to 1023 values, right? A signal without conditioning, without any changes from that sensor to the PIC pin, if you don't change that, then essentially you're going to get only the range from 0 to 1023 times 0.2 divided by 3.3, right? Much less values. So your resolution is not going to be 10 bits of resolution, it's going to be much less, right? So if you don't want to do that, one way of doing it is to condition the circuit. So if this is coming from your sensor, circuit, and this is going to your PIC pin, and for now let's assume that your sensor goes from 0 volts to some other values. If the offset is something else, we'll have to deal with that later. But this is going to be one circuit that takes care of scaling the input signal to the output value. Now, the way that an op-amp works is that it makes sure that the voltages here and here are kept at the same level. Okay? And there is no current going in to the op-amp here, right? So the current going in is going to be 0. So essentially what it means is that you have a current I that goes over here, right? And basically when your pick, starts sampling, this I is going to go over there. Now, if you look at your V out, you basically have a voltage divider circuit, right? The voltage here is going to be the same as your Vn, right? So if you have the same current going through that, you're basically going to first solve the equation up to here. So basically your I R1 is going to be Vn. Solve for I. That means I is going to be Vn divided by R1. Now, what is the V out? V out is going to be I R1 plus R2, which is going to be R1 plus R2 divided by R1 times Vn, which is equal to 1 plus R2 over R1 times Vn. And that's this equation that you have here. Okay, so this is called a scaling circuit. And you would basically pick R1 and R2 values that do exist in your set of resistors that you have at home or can buy online, and get this value. So you might not be able to make this exact, but that's the equation that you have to use. Okay, so this is an example. Suppose your transducer or sensor output voltage ranges from 0 to 200 millivolts. You want to change it to 0 to 5 volts. And the solution that they have is V out over V in minus 1 is going to be 24. So basically they take this equation, solve for R2 over R1, and they get a 24 ratio. So choose 240 kilo ohms for R2, 10 kilo ohms for R1, and that's going to be that. So I suggest that you do this at home. Go from 0 to 3.3 volts and find R2 and R1 to do this scaling. There's going to be summing circuits. So this is a sum circuit, and if again assuming that there is no current going to go in here or on this pin, if this is grounded, then this essentially means that at this point you have 0 volts. Right? And if you look at your V out, essentially whatever currents that you have, if this is current I, then your V out is going to be minus I times RF. Alright, this is ground, this is your positive voltage, so your V out is going to be minus I RF. And if you look at I is going to be I1 plus I2, which is Vn over R1 plus V1 over R2. So V1 is the voltage that you are going to provide, and that, for example, could be 3 volts, 3.3 volts, minus 5 volts, whatever. Right? So you have flexibility in picking R1, R2, RF, and V1. So if you combine these two equations, then you would get V out equals minus Vn RF over R1 plus V1 RF over R2. Okay? So basically you're able to add two voltages with scales. Your Vn and V1 are added with these scaling factors. Why is this useful? We'll see that in a moment. This one is a negating of a voltage. So again, no current here, no current here. This is going to be 0 volts. So basically you're picking the same R0 here and here. So basically your VM is going to be minus Vin. You put them all together. So you have an inverting circuit. So your Vin becomes inverted. You get minus Vin. Plug that minus Vin here in R1, R2, RF. You would get V out is RF over R1 Vn minus RF over R2 V1. Now you can use this to do a shifting of the level. So if you want to map, let's say 100 millivolt to 400 millivolt signal to your 3.3 volts and 0 volt, then you can use this circuit, plug in the values so that you can do this and get rid of the offset. So one example is shown here. So it says choose appropriate resistor values so that you can shift the voltage range of minus 1.2 volts to 3 volts to 0 to 5. So basically what you want is you want to plug in your 0 volt here and your minus 1.2 volt here. That is going to be one equation. And then you want to plug in 3.3 volts and that 400. Oh, sorry, I'm mixing up the example here and on the next slide. On the next slide, it's 3 volts. So you want to map it to 3 volts. So these are going to be the two equations that you need. So the two equations, you write them. Now note here that you have two equations, but you have 4 unknowns. You have V1, R1, R2, RF. Right, so you have a lot of flexibility in picking the values as you wish, and here is one choice that they used. So they used V1 equals minus 5 volts and picked R0, R1 to 10 kilo ohms, solved for R2 and RF, and these are the values that they got. Right, now why did they choose minus 5 volts? Because on the PCB board that they had minus 5 volts available from the power supply. If you don't, then use 3.3 volts or 3 volts or 1 volt or whatever that is available to you. Okay, so these are the equations that you would use, and this is the circuit that you would choose to basically connect your sensor to your PIC AD0 pin, so that pin can just assume that the range is from 0 to 3.3 volts, and you would indeed get 23 distinct points between minus 1.2 volts and 3 volts. So your resolution is indeed going to be 10-bit resolution. Here, if you map them, then you're going to map 1023 points between 100 millivolts and 400 millivolts, which gives you a lot of resolution, and that's going to be very useful. All right, let me skip here. Let me stop here because these are going to be PIC 18 specific, and essentially it's going to give you a procedure for doing it, and we won't need it. Later on, I'm going to use this temperature sensor example in class so that we can write a C program to do the conversions here. So skip the code that is used or any specifics of the PIC 18 chip here, but these examples would probably be useful. So take these, but don't take, I guess you could even take these as the parameters that you want, but these are going to be the kinds of examples that we're going to solve in homework and in exams and so on. All right, thank you. Let me stop here.